So who you're starting with?
All right, let's start by discussing the puzzles. Solutions for the previous one, anyone? I know you all have been agonizing over it for the whole weekend, so you must be ready to throw out some solutions. Yes. Why is that?
Because it has to be right, because you can't be lying. You can't be a right, because if he says that, then that means it is a right. It means B is a right, and that means something. So you cannot be lying.
All right, so happens to be correct, right? If basically if A is a knave, then the statement is true, and knaves can't tell the truth, right? So it's a contradiction. It has to be a knight. So then, if he's a knight and it's true, that must mean that the other guy is a knave, right? So, all right. Now let me throw out another variation of the puzzle. Now, before you guys dig into this, let me just make a quick mention of an idea from formal logic. The basic idea is that in common colloquial usage, when we say or, something or something, it is not exactly clear what we mean, right? It could be we mean one or the other, but not both. Or we could mean one or the other or both, right? And depending on the context, we can infer which one it actually means, right? As far as formal logic goes, when you just say something or something, this means an inclusive or. In other words, it is possible if one is true or the other is true or both are true, the statement is considered to be true. Right? Whereas the only way an inclusive or can be false is if both halves are false. Right? And there is a separate exclusive or specifically denominating the case where we want it to be one or the other, but not both. Right? So if we draw a quick truth table, let's say P or Q, for example, right? Then if P is true and Q is false, then the whole statement is true, right? So one or the other is true. P is false, Q is true, the statement is true. Q is true, the statement is still true. Now, only if both of them are false, the whole statement is false. Right? So how many of you have had in logic classes? Right, so you should be familiar with this device of the truth table. All right, so in this case, I just wanted to be clear that when the statement has an or in there, this is an inclusive or. It means if one or the other or both are true, the statement as a whole is considered to be true. And the only way it can be false as a whole is if both components are false. Right? Any questions? Is clear? Okay. Now go ahead and see what you can do with this logic. You ready to move along? Okay. All right. So last time we were discussing some stuff about a normal distribution. Have you guys done some reading about the normal distribution that I asked you to do in the announcement? And raise your hand if you have not done any reading about it. Raise your hand if you have done reading about it. All right. Good stuff. Okay, so at this point, right, we have an idea of what the normal distribution is representing, right? It's a continuous distribution that demonstrates how likely a particular set of values is to occur if you're basically generating a random sample of 10 times, right? So we could be measuring anything, like maybe we could be measuring the heights of people who are passing by on the street, and maybe you could be measuring, I don't know, the rainfall over a particular area for some time period, or in our case, we could be measuring returns of assets over time, right? And we'll have some kind of distribution of measurements as to how likely a particular value is to occur, right? So in general, it will, the exact shape of the distribution doesn't really matter very much. Right? The basic idea is that we have most of the probability mass sort of clustered around a particular area, right? So in general, we may have something looking like that, which means that it's relatively likely that if we conduct these measurements for an observation and figure out what's going on, it's very likely that the measurement will be somewhere in this range, right? A lot of most of the probability mass is right in here, right? And it is relatively unlikely that when we just take the measurement discover something over here, right, or in the plane, because there's very little probability mass over this probability, right? And the further away we get away from this central ball in the distribution, less likely it is that we will have a movement somewhere in there, right? Now, to be precise about it, the normal distribution doesn't have an infinite range, right? So even though the bulk of the probability is in here, it doesn't mean that there is absolutely, there is no end to this long tail of the curve. It just keeps approaching zero for all infinity, right? So we could take some, some range over here and say, what's the probability of getting a measurement here? Still not going to be zero. Now, we already talked about infinitesimally small probability, right? So once you get way out there, it's really, really small, so it's not really very feasible to actually get the measurement there, right? But mathematically speaking, right, the distribution has an infinite range. So, in other words, anything is possible, type of thing, right? So, one measure that is particularly important for any random variable, and that you're probably all familiar with, is the mean, right? Also known as the average, also known as the expected value. Right? In other words, if we take a bunch of samples over time and we average them together, what's going to be our average value, right? Just as we talked about expected value of getting $120 payout, because it's many times, it's the average value. This is the idea of the mean of the distribution. So for a normal distribution, the mean is symmetric. The mean is going to be right here in the middle. So if we take a bunch of samples at any time, our mean is basically going to be here. Right? Now, in reality, take 100 samples, it's not exactly, it's not a low-shadowing sample size, so our mean could be somewhere, off a little bit, right? But, if you have to make a best guess on what will be your mean if you take some of your samples, your best guess is going to be this, right? It's not going to be exactly there, but, you don't have to put it together. Right? For a probability, for a discrete probability, you don't have to find the expected value, right? It's just the probability being an average of all the possible outcomes of kind of curve. Right? So for our binomial distribution, our outcomes range from 0 to 100. We know exactly what is the probability of each one. So we can just say, all right, so the expected value is going to be the sum of the probability times the average. Right, now for a continuous distribution, there is not a finite number of outcomes that can happen, right? So let's say if we're talking about asset returns, right, we have some kind of distribution of the returns, right? So we might have maybe 15% over here, 20%, etc. There's no discrete number of items that can occur, right? Because we have a real line here, it can be anywhere. There's infinite number of things that can happen, right? So for continuous distribution, this really translates more into an integral of the probability times the outcome. Again, you don't really need to worry about it for our discussion, just giving you some ideas for those of you who know about basic calculus, years of integrals and stuff. And so for a continuous distribution, it's going to be the outcome times the probability density function, right? Which is measuring the regular probability of each particular value. But it's the same idea, right? Integral, the big S stands for sum, right? So we're in effect just using an infinite sum of really small bits of the area under the curve, right? So this is the idea of the mean, right? Which is where we expect to end up. So we have to make a best guess, right? Now another important metric of distribution is the variance. So yeah, it's very good. And so are you guys familiar with the idea of variance, what it really is? No is fine. It's good. It's a yes or no answer. If you say no, it's a perfectly good answer. Just want to know how many of you have, have committed before. Alright, so the basic idea is that variance is a measure of the dispersion of the distribution around the mean. Right? So, for example, this particular distribution, for our value, has a particular, weight, right? So we can have another distribution that is maybe y or something like that. You can see that this is how a large dispersion around the same mean. Right? So if we draw a sample from this distribution, we know it's going to be roughly around here, right? So now that relatively small, if we draw a sample from this distribution, it is not unlikely that we'll end up somewhere over here. It still has a pretty high probability. Right? So the variance gives us the measure of how wide dispersed the distribution is around the mean. Right? Now for a normal distribution that has a particular functional form, and there are certain regularities as to exactly what the variance of the normal distribution means as far as the probability of things happening. Right? So for different distributions, variance has a different meaning as far as how wide the distribution will be and what the shape will be. But before we get on, so variance is actually measured as the average square deviation from the mean. Right? So, and so when we take a look at variance, we just want to say, on average, how far away from the mean are we going to be? If we just pick a random value of our random variable, see where we end up, right? Because on average, how far away from the mean will we be? And that's a measure how you square the distribution, right? So, let's say, we pick a value here. Say, how far away is it? Well, if the mean is here, it's 50%, right? And this value here is less than 70%, right? And then the deviation from the mean is 2%, or 0.02%, right? And if it happens to be over here at maybe 50%, the deviation is also squared, 0.02%, right? So for a discrete distribution, we know that we have some number of points that can actually occur. And we can actually measure the deviation from the mean for each one of these points, right? So we can say, okay, the average deviation from the mean is the average of all of these deviations. Now, as it happens, if you measure this deviation, it's going to be 2%, because we're 2% above. If you measure this one, it's going to be minus 2%, right? The deviation is deviation is sign value, right? Whether above or below, right? So if we have a symmetric distribution, and you can see just immediately, if you take the average of all of these, then you end up with 0. Right? So the average of minus 2 and 2 is 0. The average of minus 3 and 3 is 0. Right? So if we just ignore everything and say, let's just take the average deviation, we're going to end up with 0 by definition. It's not going to be a very useful measure of deviation, right? They're all 0. Right? What does it mean? Nothing. Right? So as a result, instead what we do, we could just take the mean absolute deviation, right? The absolute value of the deviation. But for certain historical reasons and reasons of mathematical practicability, what we instead do is we square all the deviations, and then we take the average. You of course remember that whether we square a negative number or we square a positive number, we end up with a positive number, right? So squaring something is sort of a poor man's way of taking the absolute value. Not really, right? But for our purposes, that's one of the major effects of squaring something is we don't have to worry about the positives and negatives canceling out, because everything becomes a positive measure of deviation, right? So the variance is the average square deviation from the mean. Now it is measured, of course, in square units, right? So if this is percentage return, you take a square the average square deviation, 3%. So that should be like 10 squared percent. doesn't have very a lot of intuitive meaning, what it means for something to be squared unit. So what we actually do is we take the variance and then we take the square root of the variance to find the standard deviation. The standard deviation is roughly equivalent to just the average absolute deviation. So the square root is the average and we take the square root, right? Not exactly equivalent, but different things have different weights, different probabilities. And of course, higher deviations have a higher impact and the square function is less. But roughly speaking, the meaning of the standard deviation is the measure of the average deviation from the mean. Now, again, you don't have to worry about the mathematical details, it's not a statistics class, but I want you to have an idea and a feeling for what these things mean, right? So, any questions so far? Okay, so as it happens, if you look at historical pattern of returns of, say, equities over time, you will find that the mean return is approximately 10% on an annual basis. And you'll also find that the standard deviation of returns is approximately 15%. Right, so now that we know what mean and standard deviation are, loosely speaking, right, we know what that means, right? What is the distribution of returns, right? Because every year that passes by is an observation from this probability distribution of asset returns, right? And so what this means is that, we put some money into some investments, and we don't know what the return is going to be. Right? Now we said that the expected return is approximately 10%, but it's not going to be exactly 10%, right? Yes. So the mean is the measure of where the center of the distribution is, what on average will happen. Standard deviation is the measure of the dispersion of the distribution. Right? It's how far away from the mean on average will be. Right, so variance is the square deviation, and standard deviation is the square root of the square deviation. Right, so if it will help, let's, for the discrete case, right, the variance of some random variable, right, it is the weighted average, weighted by probability, of the deviation from the mean square, right, this is the variance. Right, so at each observation, you have the deviation from the mean. You square it, and then you take the probability weighted sum of all possible deviations, right? That will be the average square deviation, right? So you see how basically this is a measure of how far away an average, measured in square units we are from the mean, and we just take it around the value and see where we are, right? On average, will be this far away, as measured in square units. The square unit is kind of soft, right? And so we say, okay, now we have standard deviation, and that will just be the square root of the variance. Right, so now we're back to normal units for the measure of deviation. But there are different numbers that they tell us the same thing on a different scale, right? So one of them is measured in square units, one of them is measured in regular units, but they're both measures of, on average, how far away from the mean are we if we just draw a random volume from our distribution. Right? And the more dispersed the distribution is, the further away from the mean we're going to be on average when we draw around the line, right? The more concentrated it is, the less likely we are to be far away. Right? Any other questions? And please feel free to, pipe up and let me know if you need something. Okay, so as far as an actual historical observation of return, what you see is, again, the distribution comes like this. There's a mean of about 10%, and the standard deviation of about 15%. Right, so for a normal distribution, there is actually, we have a particular functional form, and that means that you can tell that regardless of what the distribution is, regardless of what the mean and standard deviation are, we know that the about 68% of the total probability of the distribution falls within plus minus 1 standard deviation. Alright? So if returns were in fact normally distributed, and we have the mean of 10 and the standard deviation of 15, that means 68% of the time, or 68 out of 100, right? So it means our return will be between 25% and minus 5%. Right? So this just follows out of the actual shape of the normal distribution. Right? So it doesn't matter how dispersed it is, right? Because the standard deviation is measured. Right? So it always will have that 68% of the total probability falling within one standard deviation of the mean. Right? And again, in a similar way, we can also determine that if we always have about 95% of probability within two standard deviations. So that means it will be 95% within minus 10%, and what is that? That's 40%. And really, and because the distribution has a particular functional form, we can figure out what is the probability would be within one standard deviation, 2, 3, 4, 5, etc. And obviously, once we get out to say 6 standard deviations, we're out to something minus 10 probability of being outside, right? So because the tail of the normal distribution fall off relatively quickly, right? So we're relatively good in tail. Any questions so far? Is this making sense? Right, so we're trying to get a handle on sort of more exactly what we can expect, right? If we'd like to invest some money and some equity, and just what can happen, right? Because we talked about the mean, right? It's about 8 to 10% closer to 10, right? But what are the other parameters of the distribution? Right, we know that it's not going to be just at 10% all the time. What does it mean for us? What does it mean for our investment returns over time? What does it mean for our portfolio in our retirement accounts over the next 50 years? And things like that, right? So this is kind of what I want to give you an idea about. Okay, so we already talked about the mean and the variance and the standard deviation of actual asset returns, historically speaking, right? So here is a quick bonus question for you, right? So we said that the standard deviation of asset return is 15%, which is 0.15, right? What about the variance of asset returns? Can you find what the variance of asset returns is? Indeed, all right, because we know that standard deviation is square root of the variance. So to find variance, the square of standard deviation is the variance, right? So it'll be 0.15 squared, whatever that's right? Everybody with us? You buying that? Right? Just a quick little test to make sure you guys are with me. Okay. So one thing I want to mention is that actual historical asset returns do not seem to actually follow a normal distribution. The tails of the asset return distribution are fatter than what we would get with a normal distribution, right? So this measurement of how fat the tails are is called kurtosis, right? So excess kurtosis means that the actual distribution of asset returns has fatter tails, which means it is more likely to get extreme values. Right? So for a normal distribution, it's really unlikely we will get some extreme value, right? So for example, if we look at the normal distribution, we know what is the probability of getting minus 50% or minus 40% return, right? So we say, okay, so here we are, we're 95% of the standard deviation, that means minus 35 we're within, and plus 55 we're within. Through standard deviation, now we're about 99%, right? And so then we get another minus 50, that's minus 50 here. Now we're within 1, 2, 3, 4 standard deviation. And like, we're being really, it's really unlikely. But actually, the stock market has lost about 40% more often than you would expect during the normal distribution, right? And basically, it really depends, right? It really depends here. In real life, like in actual observation, it happens more often, right? Both on the top and on the bottom, it happens more often than you would expect if the returns were actually being won from a normal distribution to a mean standard variance. Right? So again, that's one thing to keep in mind. Like for us at this point, you don't really have to worry about it as far as like actual results. Just know that the normal distribution doesn't actually completely describe the distribution of possible asset returns, right? There's a tail risk, the possibility of something far away from the mean happening is more likely than we would think if it was normal, right? So, okay. Now let's see. Bring up some stuff. Yeah, see that. Okay, so let me just show you some stuff. So, for example, let's say we want to plot the normal distribution, right? The standard normal distribution is mean zero variance, variance and standard deviation being 1. Right, so it's a distribution centered around 0, right, and it has a standard deviation of 1. So this is called the standard normal, which is like we have convenient values for the mean and the variance, right? So let's generate a sequence of some values, and we're going to plot what the distribution is over some values. So let's, for example, start with go from -6 to +6, right? So minus 6 is 6 standard deviations away from 0, right? So it's 6 standard deviations to the left of the mean. And +6 is 6 standard deviations away from the mean on the other side, right? So it should pretty much cover most of the probability mass that there is for a standard normal distribution, right? So, okay. So we'll generate a sequence from -6 to 6 with a step size of 0.01. Right? So guess what? Guess what the length of x is? Right? We just generated the sequence from -6 to 6 with a step size of 0.01. You don't have to guess it. Any suggestions? Actually, if I generate a sequence from 0 to 10 with a step size of 1, what is the length of the sequence? Well, the length, the number of items in the sequence. Think again. Off by 1 error, come on. 0 to 10. 11, right? So because it has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There's 11 items in the sequence. Right? So then I say if I generate a sequence from 0 to 1 with a step size of 0.01, what is the length of the sequence? 101, right? So we have a 0, and then we have 100 steps by 0.01 to get to 1, right? So now if I generate a sequence from -6 to 6 with a step size of 0.01, how many items are in the sequence? So there is 101 in each one, but we're going from -6 to 6, so how many are there? Multiply them out, right? So there's 100 in each one, and there is 12 units from -6 to 6. So how many do we get? 1,201, right? There we go. Right? Because we get 100 in each one, and then we have an extra bit for the starting point, right? So, I mean, if you can see, right? Length x, 1201. Check it out. We were right. Pretty awesome, right? And then if you want to take a look at what x is, you can see it's just a bunch of numbers going from 0 to 6 by 0.01, right? That's what we're doing. Right, now we're going to figure out whether we're going to plot the probability density function for the normal distribution over this range, right? I'm using R. It's a statistical programming tool. It has a lot of awesome stuff in it. Particularly awesome is the fact that we can work with whole vectors and matrices of data, so we don't have to deal with like each one individually. Right? So for example, now I have this vector of 1201 numbers, right? And I can pass this whole vector into the function that tells me what is the normal probability density at a particular point. And it will spit out a result with probability densities for each one of these points. Right? So instead of doing it one by one iteratively, I can just pass the whole vector in and I'll get a whole vector of results back. And I can just plot it. And I'll have a nice plot of the normal distribution. Right? So plotting is pretty easy too. You use the plot function. Right? Now before we use the plot, so the dnorm function gives us the normal density at any particular point. Right? So for example, if I want the normal density at, say, the point 1 on the horizontal axis, I want to know what is the value of the probability density function for the standard normal around 1, right? It will tell me what it is, right? I'll buy that. So I can pass the whole vector x for the, to calculate the value of the normal density function at all of these points, and it will give me back the whole vector of probabilities at all of these points. And you can see that once we get out to 6 standard deviations out, we're looking at some pretty small probabilities, right? So now let's see how it looks graphically speaking, right? So we'll plot x versus dnorm x, right? And yeah, for now we'll leave it at that. Right, so there is a plot of the normal distribution, right? You can see, so it looks like that. So the probabilities are really low once we're way out over here in the tail. You saw when we looked that we're looking at E minus 07, E minus 08, minus a really small probability to end up over here at 5 and 6 standard deviations away from the mean. The same thing on the other side as well. Right, so this is our normal distribution. So you can see it has really thin tails, right? Once we get out a couple of standard deviations, right? So this is 0 to minus 2, 0 to 2, right? So we have 95% of the probability mass within 2 standard deviations away from the mean. So if we're drawing samples from this distribution, right, 95% of the time, we're going to be somewhere in here. Right? Any questions so far? All right. Now let's just clean this up a little bit. With all these points. Then we plot we have a line here. Now, for comparison, right, there is a bunch of other distributions. One of the common distributions we can use that has fatter tails is the t-distribution. Now, you don't have to worry about what it is, but just let me give it a plot on top of the normal so you can see what I mean by having a fatter tail, right? So we're going to plot x versus the dtx here to be the freedom equals 3. And we'll give it a color of red. And then we type. And that should give us, oh yes, we got the parentheses. There it is. Right? So you can see, I mean, you can't really see the red color because the projector isn't very crisp in showing the colors. Right? But so this is our normal distribution right here, right in black. And this is our t-distribution in red. Right? So you can see here that the t-distribution has a lot more probability mass over here in the tail. Right? So if we were actually trying to generate more realistic realistic samples of returns, we wouldn't really want to use the normal distribution, and we want to use some distribution with fatter tails that will be more representative of extreme values happening more frequently. Right? Any questions so far? All right. Okay. Again, for simplicity, we're going to use the normal distribution to draw samples of returns rather than some other distribution like t or anything else with fatter tails. But just keep in mind that if you were trying to do this, do some kind of simulations in a more professional setting, you would not want to use the normal distribution because that would underestimate this tail risk of extreme values happening, right? But for our purposes of just kind of getting an idea of what happens as we get as we draw samples of returns from what the investments are doing over time, and how that affects the value of our investment over time, and the value of our investment accounts over 50 years, something we might be interested in if we're thinking of saving money for the future, right? It's a good enough tool to just see what happens, right? Okay, so you might remember that with our initial demonstration of what happens with investment returns, right, was this. We just said, let's assume that we have a 10% return, right, and we're putting in some money every period, and it just grows at 10% until we reach the end of 50 years. And then we just figure out how much we have at the end in our account. It's like $6.5 million. Now, if we're using, I generated the plot right here in R, right? It's basically just one line of code to generate it. Because what we do is we have, we're putting in 5,000 every period, and that 5,000 grows at 10% for a variable number of periods from 1 to 50, right? So we just, so if we were to generate how much money we'll have from each one of those $5,000 investments, we put in 5,000 and we multiply by 1.1, right, which is a 10% return, and we're going to produce a vector of total investment returns by raising it to the power of 1 to 50. Now, before we run that, right? So this syntax for integers, right? 1 colon 50 will generate a sequence of values. Right? It will be a vector of values 1, 2, 3, 4, 5 out to 50, right? Now, because R runs vectorized operations, when we do 1.1 raised to the power of the vector 1 to 50, we'll generate a vector of 1.1 raised to the power of each of 1, 2, 3, 4, and 5, right? So it'll be 1.1 to the 1, 1.1 squared, 1.1 cubed, all the way out to 50, right? So it'll be a vector of these values. And that will be the return that we get on each one of our $5,000 investments over time, right? So the first one we put in will be 5,000 times 1.1 to the 50th, right? Because it has 50 years to grow. Second one we put in will be 5,000 times 1.1 to the 49th. And so on and so forth until the last one we put in, we get only 1 year before we start counting, right? So right here, we generated this vector of factors of 1.1 to the various powers by using this syntax. And then we'll multiply each one of them by 5,000, because we're starting with 5,000 for each one. And that will give us a vector of values for each one of our $5,000 investments over time, right? Any questions? Any clarification needed? What we're doing? What's going on? Okay, so let's run that and see what happens. So there we go, right? That's a vector of 50 items, right? So you can see the first one is just 5,000 times 1.1 to the 1, which is $5,500. And the second one is 5,000 times 1.1 squared, which is $6,050. And so on and so forth until we get out to 5,000 times 1.1 to the 50th, which is 586,000. Right? You might remember these numbers because we calculated some of them when we were discussing that graph of investment returns and investment values in, say, retirement accounts with regular contributions, right? And we discussed how the last one, gives us more than $500,000 because it is the one that comes from the 5,000 we put in today, and it grew by 50 years at 10%, right? So now we might say, well, how much do we get in total? Well, guess what? We have this vector. We can just sum all the values of this vector, and we get 6.4 something million. Right? So that's where the number came from. That if we have a 10% stable return, we put in 5,000 every year, and we wait for 50 years, that's how much we'll have. Right? It's just a sum of the different values that will generate by each of the $5,000 investments. Right? And of course, we can plot that. Instead of saying sum, we can just do plot. Right? And there is our graph of the investment values for each of the $5,000 contributions. And we can get rid of H for sort of the height bar, and there it is. Same thing. Just a different representation of the same number. Right, so now what we want to do is we know how to generate this information given a fixed return, like 10%. Now what we want to do is we want to modify this. So instead of having a fixed 10% rate of return every year, we draw samples from the distribution of returns with a particular mean and standard deviation. Now in our case, we're going to be drawing sample from a normal distribution with a mean of 10%, because as we discussed historically, equity is returned at 10%, and a standard deviation of 15%. Right? So instead of having a fixed 10% return, we'll just have some kind of random drawing from a distribution of possible returns, and see what how these variations can affect the total value of our investment. Right? So first of all, right, let's get back here, right? So how are we going to do this, right? First of all, we need to generate returns for 50 years worth of time, right? So again, R has very nice and convenient functions for drawing samples from various distributions. Right, so let's, for example, for normal distribution, it's called R norm, to generate random values for a normal distribution. And so let's say I want to draw 10 samples from a distribution with a mean of 0.1 and standard deviation of 0.15, right? So what happens? Well, there is some investment returns, right? Just like a random sample of possible investment returns from this normal distribution. So what we're going to do is generate 50 of these, a time series of 50 possible returns, right? So there we go. We can do this pretty easily. Instead of saying 10, we're going to say 50. And there is, a sample of 50 random values from a normal distribution with mean 10% and standard deviation 15. Now what we need to do is we need to convert these numbers into cumulative returns for each of the $5,000 that we put in. Right? So, what's going to happen, right? So the first $5,000 is going to grow by minus 18%. It was a bad year. And then we grow by 21%. Then we grow by 1%, 1.9, 2%, etc., right? So how do we grow by all of these percentages, right? So let's come back to our discussion of compound growth. All right, so 5,000, we start at times 0, right? 5,000. So in the first year, what will happen? We'll grow by minus right? So how do you go by minus 18%? You go by 1 plus the rate, which is minus 18%. Right? Okay. So we'll end up with, so at this point, we'll end up with some amount which is right? So then this amount, whatever it is going to grow by the next rate of return that we have, which is 21%. Right? So we're just going to go by 1 plus 21. And that will give us some amount, whatever that happens. By the next year, this amount is going to grow by 1 plus 50%. And so on and so forth. Right? So you can see that it doesn't have to be the same as the end of the day. What we have is we have 5,000 times 1 plus R1 times 1 plus R2, etc., etc., until we get to 50, and that will give us the cumulative amount that our initial 5,000 has grown to until by the time we got to year 50, right? They don't all have to be the same, but we know what the rates are, we can figure out what we'll have as the end. Right? So, okay, and so then, the second 5,000, we're going to put in right here. Right, so the second 5,000 is going to go by 1%, 2%, etc. And so on and so forth, right? We're going to insert the 5,000 in every step of the way, right? And we'll have different growth patterns for each one. Right? Makes sense? Any questions? Do you understand what we're doing here? Okay. So how are we going to generate these sort of product of 1 plus whatever? Well, first of all, the easy part. Let's just add 1 to all of these, right? So, if we generate, and again, every time we generate a random sample, they're going to be different. And so if we wanted to generate them and keep them as they are, we would just save them in a vector and then use that vector, right? So for the moment, let's say let's store some of this stuff in a vector so that we can kind of look at what exactly is going on with our values. Right? So that was our x. Right? Now x is again two vector of other returns. All right. So we say, okay, well, what we want to do is we want to add 1 to each one of these. So let's take advantage of vectorized operations. All right, so 1 plus x is just 1 plus all of those guys. Right? Now the next thing we want to do is we want to generate, sort of partial products of different subsequences of these 1 plus the rates. Again, there is a very nice function called cumulative product. Right? So it generates a vector of product, but they're all partial products. So the first one will just be itself, second one will be 1 times 2, third one 1 times 2 times 3, etc. Right? So this is like sort of accumulating the product over all operations. So let's take cumulative product of 1 plus x. Right, so the first one is just itself, right? You can see there it is, just itself. Second one is this times that, happens to be about 0.96. Third one is this times that, happens to be this, etc. Right? See what's going on. Now what we want to do is we want to multiply 5,000 by each of these cumulative products, right? Again, this being a vector, we can just multiply it by a constant of $5,000. Alright, so there we go, take it back, and so we take 5,000 times all of that. And so those are the values of each of our $5,000 that we put in over 50 years. Right? So the first one is about 3% more, there it is. Right? The second one is about 4% less. bad year. And bad second year, you got the negative 7% return, right? So you can see, right? So we were just multiplying 5,000 by each of these cumulative series of returns multiplied together, right? Yes.
But is that usually only for the first $5,000, or is that with adding $5,000 in every time?
Well, this is for each of the $5,000, right? So the first $5,000 that we put in gets to grow by all of these periods, all 50 of them. So the first $5,000 just by itself, without putting nothing else in, turns into 2.036 million. Now the second $5,000 gets to grow by 49 periods. And so the second 5,000 just by itself, without everything else, turns into 1.7 million. Right? And so on and so forth, whereas the last $5,000 turns into just a little bit. Right? So we're looking at each one of those individually in this vector. So of course the total amount in our account is going to be the sum of all of that stuff. Right? So again, if we want to know the total amount of, so first of all, we can plot this, right? Right, so there is a plot of the different bits of our investment for over time, right? So this is the first $5,000, it gets to grow by a lot, right? This is the second one, this is the third, etc. And so this is the last one that didn't get to grow much at all, right? So you can see that now that we can basically generate a sequence of values for our investment over time with basically running just one line of code, right? We just generate a sequence of 50 returns, we add 1 to all of them, find the cumulative product, multiply by 5,000, and there is what we have in our retirement account at the end of 50 years with that random sample. Right? Make sense? Okay. And so now, if we're curious, we could say, well, let me find the sum of what all I have in my account. And check it out, you made $20 million. Lucky. Right? So, if we just have a steady 10% return, we know that we'll get 6.4 million. Now here we happen to luck out and we got 20 million. How often is that? Right? Now it's possible we can get less lucky and maybe we'll get less than 6 million. Right? So let's just try and generate some of these and see what they're going to look like. Right? Okay. First let's do the plot. Now our x is just a sample of 50 random values from the normal distribution of mean 10 and standard deviation 15. Alright, so we want to generate fresh ones every time. Alright, so let's just generate fresh 50, mean 0.1, standard deviation 0.15. Alright, then we add 1 to that, then we take the cumulative product, then we multiply by 5,000, and then we plot. Alright? So every time it's going to look a little bit different. You can see how here we got a little lucky, so the last one is way over there, about 2 million. Right? So pay attention to what happens, right? Because the plot is going to automatically rescale the vertical axis depending on the range of values that we have here. Alright? So let's just take a look. We'll just plot another one here. Alright, so that's another possible sequence of returns. So now we got up to 60 plus 05, which is how much? $600,000 or so, right? So that's about on par with what we got. We just had a 10% steady, right? Because we got 580 something, about 600,000. Right, so you can see that we can really do this all day, right? There's another one. We only got up to 400,000. There's another one. We only got to 150. We were very unlucky, right? Now, I mean, if we add all of these up, we're still probably at about like $1.5 to $2 million. It's not bad, but it's just worse than 6 million, right? So, we can do this all day and generate a bunch of these, right? And they're all different. You can see the graph dance and the axis change scale and all that, right? And so we can actually generate, we can look at the sum of what we'll have in our account with a bunch of random samples as well, right? Instead of doing plot, we could just say, sum. And then we could type for sum. Right? So we made $5 million. We made only $1.4 million. 1.1, a really bad sample. We made 5.9 million, 4.2 million, 8.2 million. Right? So you can see that there's variation in what the actual outcome is going to be, because these things are random. Sometimes you get some sequence of really good returns. Sometimes you get a sequence of really bad returns. Most of the time, you're going to get a sequence of sort of average returns. Right? And you don't really know what's going to happen in the next 50 years. Right? But either way, even in the relatively bad cases, you still end up with a fairly sizable chunk of change in your savings, right? So that's basically the idea. You shouldn't, just because in some particular year you're going to see bad returns, or a couple of years you have recession and you have bad returns, which doesn't mean that OMG, I'm just taking all my money out, I'm not doing this, right? Because these things happen. This is a source of there's random variation in what's going to happen, right? But over time, as long as overall our economy is still productive and the firms you're investing in are creating value, on average you should still be making out pretty well, right? So this is the basic idea, right? In order for you to really get really screwed, something really, really unlikely has to happen. And if you recall with our earlier discussion of the binomial distribution, it's sort of like drawing tails 50 times, right? It's not very likely to happen. So on average, as long as the mean is a positive rate of return of 10% or so, on average, you're going to be doing pretty well, even if some years might not be very good. Right? Make sense? Okay. Now let's let me see. Now let's throw in another kink into the problem here. You remember that last time we discussed the idea of inflation, right? And we said that, well, for us as regular stocks, right? So if you get 6-point-something million in 50 years, and inflation in the meantime is about 3% a year, well, that translates only to 2 million or whatever it was of today's dollars, right? In terms of today's purchasing power. 1.5 million or something like that. Right? You guys remember that? Like a factor of 4 point something over 50 years, 56. So you might say, okay, if I get if I happen to get 1.1 million after 50 years, and then I take into account inflation, then that will be actually only $300,000, which is not a lot at all, right? So there are a number of things that we can actually other things we can consider in this model. Number one, when investment returns are relatively low, inflation also tends to be relatively low. All right, so if you have a sequence of really bad returns, chances are, there's, unless we go all Zimbabwe and go into hyperinflation or something, right? Chances are inflation is also going to be relatively low. Number two, say we talked about contributing $5,000 every year, but chances are, as the value of the dollar goes down, the amount of the contribution every year will go up proportionally. Now, if we talk about, for example, IRA contribution, right? Currently, an IRA contribution is $5,500, which was relatively recently raised from $5,000. And if you look at it in general, the IRA contribution limit sort of tracks inflation. So we could say that if we're looking at an inflation rate of 3%, And we could also assume that every year we're going to be putting in 3% more than the previous year, right? So if instead of putting in 5,000 every period, we put in 5,000 in the first one, and then put in 5,000 plus 3% of that. In the second one, we put in 5,000 times 143 squared, and the third, etc., right? So we're increasing the actual contribution into our investment as well as inflation is eating away at the value of the dollar. All right, so in that case, we will produce a higher, you can see that if we're putting in more than 5,000, and every year we put more and more and more because the inflation is eating away at the value of the dollar, right? We'll produce more total value in our retirement portfolio than if we just put in exactly 5,000 every time, right? So, I mean, we can model that as well. We could say, let's imagine that in general, on average, IRA contribution limits are going to track inflation. So if we're assuming inflation is 3%, that means that every year we can put in about 3% more than the previous year, right? So we can modify this, this 5,000 here, right? We're just saying, I'm assuming I'm putting in 5,000 every year. Instead of putting in this constant 5,000, we can actually create a vector of contributions over time, right? So what would that vector look like? Right? So the first contribution, let's say, is 5,000. Well, actually, it's 5,500. But it's 5,000. Right? So the first contribution is 5,000. Right? So the next contribution is going to be 5,000 times 1.03, and the next contribution is going to be 5,000 times 1.03 squared, right? And so on and so forth, right? We're tracking inflation to the value of our IRA contribution. Right? And of course, at the end, we have time 49, we have 5,000 times 1.03 to 49. Okay. Right, so I mean, we could fairly easily generate a vector of these values, right? Because this is 1.03 raised to the power of 0 to 49, right? So this is 1.03. So we have a vector of 0, 1, 2, 3, 49. There's 1.03 value in this vector. We will multiply it by 5,000, and that gives us the vector of our investment contributions every year. Right? We're buying that? I mean, do let me know if something is unclear and you want me to explain. If you're sitting, I'm assuming you guys are ready. Right? Okay. So, now we're going to, so generate the vector, 5,000 times 1.03 raised to the power of 0 to 49. Right? There it is. Right, so the first one is 5,000, the second one is 5150, 3% more. The next one is 0.4, 3% more from the previous one. You can see that toward the end here, we're starting to contribute 20-something thousand, which again happens to be about a factor of 4 over 50 years, right? So we already know that 3% over 50 years is about a factor of 4 point something, right? It's the same thing here, right? Just as it reduces the value of our stash in 50 years in today's dollars, it also increases our contribution in future dollars, right? So you can see that if instead of contributing 5,000 every time, we're contributing a little more, that will sort of help offset, in part, some of the effects of inflation on the value of our stash, right? So now we'll take this vector and multiply it by the vector of investment returns, right? Cumulative product of investment returns over 50 years. Now again, R being pretty nicely vectorized, we can multiply two vectors together, right? And it will just multiply each corresponding value, So if we have one vector, now let's say 1, 2, 3, 4, and we have another vector that is say 4, 5, 6, 7, and we multiply them together, what we do is multiply 1 by 4, 2 by 5, right? We produce a vector of rank 4 with 4 root products, right? So again, it's nice, we don't have to write any roots or anything. Just multiply the vector of our contribution by the vector of the cumulative investment returns for each one. And bam, we have our final result of what we have in our portfolio as measured in the 50 years. Right? Any questions? You buying that? Okay. So let's just go back here. We have the sum, right? So there it is. So now instead of just 5,000 multiplied by the cumulative product of some randomly generated returns, what we're going to do, 5,000 is still there, times 1.03 raised to the power 0 to the 49. Right? So we're generating that vector of contributions, which are growing at 3%, and we're multiplying that vector by the cumulative product of investment returns over 50 years, right? So what do we get as a result? Oh, we just made $43 million. Awesome. Right? So, let's try that again, right? This is a random simulation, which is drawing random values. Let's see, sort of what is the range of values we can approximately expect to get, right? $19 million. It's not so lucky this time, right? But still, not bad, right? Oh, that was really unlucky. 2.6 million. I mean, we must have lost serious money there at some point, right? So, oh, look at that, $142 million. Nice. All right, so you can see basically that 2.5, 14, 72, 4.5, 12. All right, so now you can see if we correct our contributions themselves for inflation, right, we have a better chance of ending up with some reasonable amount even after we deflate it to today's dollars. And by your movements and bag gathering, I'm taking that we're done with the class for today. So.